So section 1 is about the chi-square goodness of fit test. So chapter 12 is all about
It says
Chirac right in my right notes.
chi-square.
It
Chi-square.
says Chirac.
Remember how we decided that I know how to pronounce things better than you guys, with the exception of a few select words? A few select ones, okay? Like, I taught you to say cheb-shevs and not chebby-shevs or chubby-shevs or whatever you guys say.
It's Chubby's.
Okay, this is chi-square. Chi-square. Not shy-square, chi-square, okay? Oh my gosh.
107.5.
Okay.
That's number 1 for hip hop and R&B.
You know this is being recorded, right? So people never listen to these notes
With
from
DJ
this point
Moondog.
forward.
Do you have the notes for name for sorry,
DJ Hot Sauce.
like, do you know if it's named after someone?
It's a Greek letter.
Oh, okay, that's true, but this is definitely shy.
No, like this definitely follows the chi-square distribution.
Shy.
Oh my
Took
gosh.
only 3 more minutes of class.
Poor people who are sick today and have to watch these notes unless you all argue with me, whether it's chi or shy.
Where do we watch these notes?
Okay.
Where are they?
Schoology?
Where?
Shocker.
I'm pretty sure it's Schoology.
Oh my gosh. Okay. So, we're going to do a phantoms today. It's a new type of phantoms. We're actually going to do the whole phantoms because some stuff is pretty different. Like in terms of calculating the test statistic and
Conclusion the same?
what?
Is the conclusion?
Conclusion is the same, yes. Okay. Wonderful. Okay. So let's say that I roll a die 60 times. How many times would you expect me to get a 1? 10. How about a 2? How about a 3? Okay, you get the point. I should get about 10 of each. Am I definitely going to? No. Okay. Let's say, so this is what I expect. What happens if I got this? What do you think?
There's something fishy.
Not fair.
It's probably not a fair die, right? It's a loaded die. Okay. So what's going to happen is I'm going to give you a distribution of what actually happened. And you're going to try to decide, is that distribution consistent with what I expected to happen? So it's almost like doing multiple hypothesis tests. You have to compare, did I get the same number of 1s that I expected? Did I get the same number of 2s and 3s and 4s and 5s and 6s that I expected? But it's all being done at once. So you're going to find out, yes, my sample is consistent with what I expected, or no, it's not. You're still going to calculate a p-value. So if your p-value is less than alpha, we reject the null. If we reject, that means what we observed is too different from what we expected. So then what we expected, our null, is false. So kind of like what we've been doing in the past. Okay, this one uses a chi-square distribution. So you remember that last table in your formula books that I give you that we haven't used yet? That's what we're going to use today. We're going to use a chi-square distribution. Okay, so this is the example that you guys have. Is this die fair, right? Is this what you have at the top?
Yeah.
Okay. So, I guess we're going to write parts of it. Not all of it. Okay, so the first thing that changes is P changes. Chi-square is used only for categorical data. Isn't this what we have at the top?
Yeah.
You said P change.
It's not 60.
There's some degrees of freedom in a way. It's not very free.
So you just have this.
Okay, I guess we're gonna write small then. So, write small. We're not gonna do the whole thing. Okay, so chi-square is for categorical data. So yes, you roll a 1, 2, 3, 4, 5, or 6, but that's not numeric. You get put into a category based on what you roll. So because it's categorical, we're gonna be using pi. Here's the difference, is there's more than one pi. Because there are 6 options for what I could roll, there's pi 1 through pi 6. So you're going to have pi 1 equals pi 2 equals pi 3 equals. Okay, so pi 1 is the population proportion of ones that are rolled. Pi 2 is the population proportion of 2s that are rolled. Pi 3 is the population proportion of 3s that are rolled, etc. Okay, so then your null is going to look different also. Because you have 6 pi's, you're going to have 6 values in the null. So in your null, you're going to have pi 1 equals 1/6. Pi 2 equals 1/6. Pi 3 equals 1/6. Pi 4 equals 1/6. Pi 5 equals 1/6. And pi 6 equals 1/6. I expect to get a 1 1/6 of the time. I expect to get a 2 1/6 of the time, a 3 1/6 of the time, etc. Okay. If the null is true, this tells us that the die is fair. Okay. If we reject the null, it does not mean that all of these are wrong. We're going to reject the null if at least one of these is incorrect. So your alternative is going to be at least one of the above proportions is incorrect. In parentheses, I'm going to put that tells us that the die is unfair. Okay, we're going to do a full example in a minute. I just want to jump right to the test statistic. Okay, so this is the formula for chi-square. It's the sum of observed minus expected squared divided by what you expected. Okay, so in this case, we actually observed 13 ones. Can you guys add those up and tell me what they add to? What is it? It's 100? Oh yeah, because I told you it's 100 rolls. Okay, so if we roll a die 100 times, we would expect 100 over 6 ones. So this is going to be 100 divided by 6 squared all over 100 divided by 6. Okay, and then you have to do that for each one. So 23 minus 100 divided by 6 squared all over 100 divided by 6 plus dot dot dot. Okay, calculate this right now, please. My suggestion would be to save 100 over 6 as x. What?
I thought it was chi, not x.
Not funny.
You're left.
I got 11.48. Somebody's going to need to verify that because I could have the wrong answer. Sorry, we can't be so fun. Anybody?
I got 11.
11.48. Anybody else? almost.
I got it.
11.48. Okay, I'm gonna trust Izza and Zoe. You did not get 11.48.
I did there.
You what?
I also would
Okay.
have that.
Okay.
Sure.
Next thing that's a little bit different is chi-square is always an upper-tailed test, no matter what. It's always upper-tailed. So next thing that you're going to look for is the probability that chi-squared is greater than or equal to 11.48. Okay, like the t-distribution, chi-square also has degrees of freedom. It's based off of however many variables you have. So because I have 6 variables, my degrees of freedom are 6 minus 1, so I have 5 degrees of freedom.
I got one.
Okay, good. I'm so glad. Okay, so then I believe, ignore all that. We'll go through it eventually. Okay, you guys have this. You go to 5 degrees of freedom, and you look for where 11.48 falls. So 11.48 is somewhere between here. That means that your p-value is somewhere between 0.05 and 0.025. What does that mean? We reject the null. And what do we believe about the die? It's unfair. Do we know how? No. We just know that all of the sides are not equally likely. Does this give you a general idea, a very general idea of the process?
Yeah.
Okay. I would like to do a more interesting example. Is that okay? Okay. I did not give you a whole lot of room, so I'm really sorry. Okay, so this is the next example that you guys have. The Mendelian theory states that the number of a certain type of peas falling into the classification round and yellow, wrinkled and yellow, round and green, and wrinkled and green should be in the ratio of 9 to 3 to 3 to 1. Suppose that 100 such peas revealed 56, 19, 17, and 8 in their respective classes. Are these data consistent with the model? Okay, this is a full example that we're gonna do. That's Mendel. So
He looks
just
like
so
he
you
has
know.
that Snapchat
Snapchat
filter
filter.
where your face is all condensed. Want
I
to
don't.
see?
No, I don't want to know.
I'll show you after.
I don't want to know. So thank you though.
Wait, did you do this by yourself?
Did I do what?
The example? Because there's stuff already written up there.
Oh.
Do you think I was practicing for this? It's from the last example. Okay, so in this case, for our p, we're looking at the 4 different classifications of p's. So we're going to have pi 1, pi 2, pi 3, pi 4. Okay, so pi 1 is going to be the population proportion of round and yellow peas. Of course you would write all this out, but I'm just being lazy. So we have round and yellow, wrinkled and yellow, round and green, wrinkled and green. Okay, actually write that out though. On your homework, don't write out pop probe. Write out population proportion.
For pop prop.
Okay. Now, for your null, we're going to have pi 1 equals, pi 2 equals, pi 3 equals, and pi 4 equals. Okay, these are proportions. So we're not going to write it as 9 to 3 to 3 to 1. If round and yellow are 9, it's going to be 9 out of the total. So pi 1 should be 9 out of 16. Pi 2, the wrinkled in yellow, should be 3 out of 16, 3 out of 16, and 1 out of 16. Does this make sense? Yeah? Okay, so then this tells us that the data are consistent with the model. Our alternative is at least one of the above proportions is incorrect. In parentheses, that means that the data is inconsistent with the model. Questions yet? No? Okay. Next thing, we have to check the assumptions. What do you think the first assumption is?
Random sample.
Random sample. Doesn't tell us, so we're going to say yes, assume so. Okay, second assumption is the one that's weird. So normally our second assumption is approximately normal sampling distribution. That is no longer the second assumption. The second assumption is the sample large? The way to check that is, are all of our expected values greater than 5? Okay, so the way to calculate the expected value is to do pi multiplied by n. So our first pi was 9 out of 16, and our n is 100. Did you just guess that off the top of your head? No. 56.25. Then we have 3 out of 16 multiplied by 100.
I'm not bad at that. 18.
Pi 3 is the same one, so just write it again. Here are our 4 expected values. So we can say that these are all greater than 5. So our sample size is large enough. Okay, for n, we're going to say we are conducting and it's chi-square, so it's always upper-tailed. So it's an upper-tailed. Okay, it's called a chi-square goodness of fit test.
That's gracious.
Okay, because we want to know, does our data fit the model? Or fit what's expected? So goodness of fit test using, it's called the chi-square critical values table. With how many degrees of freedom? 3 degrees of freedom. Because we have pi 1, pi 2, pi 3, pi 4. We have 4 classifications. So you subtract 1, you get 3. So this is not one where you do n minus 1. You don't do 100 minus 1. You have to look at your p. How many pi's you have in p.
Why do we need to specify that it's upper tailed when
It's always upper tailed,
well, yeah.
just for good practice, so we remember the tails. And we're going to use a significance level of 0.05. Okay. So our test statistic is chi-squared equals the sum of observed minus the expected squared all over the expected. So that's going to be 56 minus 56.25 squared all over 56.25 plus 19 minus 18.75 squared all over 18.75 plus dot dot dot. What do you guys notice? Anything? No? Okay. Are you guys calculating this too, or am I calculating it for us? I'm calculating it for us, wonderful.
I don't know the absolute values.
It says in the.
It says right on the paper.
I can't read.
Nothing wrong. That happens to all of us.
I got .658. Nobody else did it. I was the only one that did
I
it.
am still going.
Wow, you guys are the worst.
I try.
Okay, we got the general process down? Okay. Do you guys have your tables with you?
Yeah.
Okay. Get out the chi-square table. It's the chi-square table, not chi-square. Okay, so we're looking for the probability that chi-squared is greater than or equal to .658 with 3 degrees of freedom. Chi-square critical value table is the last one.
I didn't get that.
Go to 3 degrees of freedom.
I
Did not?
got .40666, but I could be wrong.
Close enough. Okay, where do you see .658 or .40, whichever one is correct? What?
Okay.
Oh, okay. Do you guys see how the first value it starts with is 4.11 and then they just get bigger?
Yeah.
What does that mean about your p-value? Greater than 0.25. So it's probably pretty big. So this is greater than 0.25. Okay, if you would like to know how to do this on the calculator has a chi-square CDF. Of course it does. Okay, on my calculator it's number 8.
Mine is C.
Okay, so you're going to do your lower bound, so .658, comma, your upper bound, 1 times 10 to the 99th, comma, 3 degrees of freedom, so it works exactly like the TCDF.
Oh, you're right.
And I got .883. You guys with me? Yeah? Yeah, we're good?
Pretty Gucci, man.
Okay. You want the good news of this test? You have to draw a diagram, but there is no way for you to know what the diagram looks like. So you're going to draw it on the calculator and then copy exactly what the calculator says. Okay?
So I don't have to think.
So let's see if I have. Okay, so here's how that's going to work. Go to list 1. And in list 1, I want you to put all of the observed values. So we actually got 56, 19, 17, and 8. In list 2, you're going to put all of the expected values. So that's what we calculated in the assumptions. And then quit out. We got that? Okay. Oh, that was really mean of me. We're not going to do it that way. We'll talk about it, okay? Thought I had something else on here. Okay, go to stat. Go to stat. Go to tests. Oh, I know why I did it this way. Oh, some of you are going to be so mad. Okay. So, right now, if you go to stat and you go to tests, my letter D says chi-square GOF test. Chi-square goodness of fit.
Yeah.
Okay. Now, unfortunately, some calculators don't have this test. Yours is one of them. Yeah, anybody that has a newer calculator should have it. Anybody that has an older calculator doesn't.
They don't.
That means you should have to do it then.
Is unfortunately for you, you don't have this.
Just do it live. Just do it live.
I got another calculator.
No, it's okay.
Just grind it out.
Did you find could you find the test statistical like we just did?
What do you?
Could you find the 0.658 by using the formula?
Oh, yeah. The
Right, like the observed minus expected squared. Could you though? And then could you use the chi-square CDF? Or the table? Could you just do everything that we just did? That's what I'm asking you to do. If I had you do it on your own, then you're fine. The only thing that you're not gonna be able to do is get a figure. So you're just gonna have to. No, you still have to do it. You have to just use your best judgment.
Oh, yeah, that's exactly what I was thinking.
Okay, so Izza,
Ages.
these figures are always skewed right. So it's always gonna be something like that.
Unless there's a high.
It's always upper tailed. And shade it so that it looks like the p-value is correct. So your p-value is 0.88, so basically shade most of it. That's all you're gonna have
All I'm gonna
to
have to do is find the p-value and then kind of just,
do. Yeah.
So if I'm like off in the whole.
Oh no, my calculator's broken.
All that's gonna be off.
Guess now.
Yeah, no, that's how I know. Okay.
Okay, so the rest of us, go to stat, go to test, and go to chi-square goodness of fit test.
That's good for you. It's actually.
Okay, observed is in list 1, expected is in list 2, degrees of freedom is list 3, and then hit draw.
Degrees of freedom is list 3?
I mean, degrees of freedom is
It's
3.
3.
Yeah, I don't know what I was.
You're on a roll.
He's on a roll.
There's no strong. There it is.
Okay, you should see something like this, except without the box plots, because I just have box plots.
I had box too. Oh my god.
Okay, it should say chi-square is 0.658 and your p-value is 0.883. Okay, so when you get to the O part of phantoms, all you have to do is copy this figure. Okay, so copy that figure, and then this is what I expect to see. I expect you to tell me that right here is chi-square equals 0.658. That's all I expect for O. Can we do that?
Can we build it? Yes, we can.
Okay, so that's the O part. You still have to compare it like to alpha, like we normally do. So 0.883 is greater than 0.05. So I'm going to fail to reject. Because I failed to reject, we're going to say, based on my analysis, I failed to reject the null.
You were polar.
As there is insufficient evidence that the model is incorrect. Or that the data is inconsistent with the theory. So this should sound just like we normally write it. The next sentence is going to change a little bit based on wording. So the probability of obtaining okay, so in the past we've always said the probability of obtaining a sample mean of a sample proportion of, in this case we have multiple values. So you're going to say the probability of obtaining the observed distribution. So that means the 56, 19, 17. So the probability of obtaining the observed distribution given the assumed model of 9 to 3 to 3 to 1 is not rare enough to doubt random chance fluctuations about 0. So that should sound pretty much like normal.
It's approximately normal.
So the main changes for this test are in P, you're going to have multiple pi's, the hypotheses, the assumptions, calculating the test statistic, and the figure. Everything else is pretty much the same. Calculating the test statistic is a little bit more difficult, but then everything else is a little bit easier, I think. So, what I was trying to get you to notice before, did you notice that the observed values were very, very close to the expected values?
Yeah.
Like really, really close?
Yeah.
Okay, those numbers, I didn't tell you, but those numbers were actually from one of Mendel's experiments. And so he presented this data, and somebody pointed that out, like, wow, your data's really kind of close to what you would expect to happen. You know, it's like, it's almost too perfect. And so that's what this was, is he actually had to admit that he just made up the data. He faked this experiment. Or at least fudged the numbers so that they would be closer to proving his theory.
So he has a red face because of that.
He's embarrassed. Everybody else got it, okay?
I thought he got like.
Okay, just like everyone else in milk normally.
A skin disease or something.